So, good morning everybody. Welcome to the MikroTik user meeting here in Berlin, the first really big user meeting in Germany. I'm very happy to have the first guest presentation here for you today. I'm going to talk about access concentrators and how to optimize their availability and performance. Ja, ich möchte diesmal auch die Gelegenheit nutzen, zumindest kurz auf Deutsch Hallo zu sagen. Wie gesagt, meine Präsentation über Access Concentrator, die wird natürlich auf Englisch stattfinden. Und ich freue mich total, dass wir endlich mal ein großes User-Meeting hier auch im deutschsprachigen Raum haben. So before I head to the presentation, I want to have a few slides about myself and our company, just a few ones, since I have quite a few examples later to show you in these 45 minutes. My name is Patrik Schaub from FMS Internetservice in Germany, and we are a value-added distributor. Means we are offering training, consulting and support for the products that we are selling, so we're not focusing on box moving. The company has been founded in the late 90s and we are situated in the southern part of Germany, pretty close to the Swiss and the French border near Freiburg. By today we have 11 employees and well, I think that's the lot for the company profile. We're offering MikroTik training since 2007. We're having an own training center at our facility. Have the first German-speaking certified trainers for MikroTik in our company. By today there are 2 trainers, myself and our leading trainer Sebastian Inacker. So if you're ever looking for training, you're very welcome to drop by and get in touch. As I said, we're doing value-added distribution. We're really offering a lot of services, and I think pretty special for FMS is that we can accompany a customer if he wants to for his complete project. So we can start with consultancy, help with deployment, support the customer's IT staff by deploying the project in the end, train the staff, and optionally offer support contracts for those parts that the customer cannot or does not want to cover himself. Our target customers are small to large enterprise customers, but we have a special focus on internet service providers and more Stadtwerke customers in Germany whom we introduce to the ISP business. Referring to or regarding today's presentation, we did already set up multiple huge or medium networks like national and global VPNs with hundreds of nodes, or ISP backbone and access networks. And as this presentation today is focusing on ISP and BRAS, for example, I think it's interesting to know that this is not pure theory, but this is backed up by years of experience in real networks. Next to those services, we're also helping ISPs with regulatory and administrative stuff like security concepts that are required by the German regulator, so-called Sicherheitskonzepte. We run TAL contracts for customers or help them to establish their LEAR with RIPE. So ISP business and all the services that belong to ISPs are what we do a lot. We have a small distributor table here. You're very welcome to drop by if you're interested in. And as always, we try to bring a few interesting things that you might not see every day, like our VDSL SFP modems that will allow you to use MikroTik as a DSL gateway without an external modem. We have the first 60 and 80 gigahertz mobile spectrum analyzers with us that are available worldwide, and they might be pretty interesting to use for site surveys in V-band for the new MikroTik 60 gigahertz gear. And if you want to, you can see a long-range Ethernet test from one MikroTik to another through a 300-meter Cat5 cables running on our SFP modems too. So drop by if you want to. And now we head to the presentation itself. Before we talk about redundancy and load balancing, I think it's interesting or worth to look at what an access concentrator really is. The term itself is not really well defined, but if you try to explain what it is, you can say in general, an access concentrator will be the endpoint for multiple connections. It's usually aggregating traffic, and quite often it's an entry point to another logical network area, like for example a gateway being the gateway for a new IP segment. There are different types of access concentrators. There are more historical ones like remote access concentrators that were used for dial-in connections with ESDN or POTS. And there are more common or actual types like the combination of LAC and LNS, layer 2 network, layer 2 access concentrators and layer 2 network servers that are still used in broadband networks a lot. And there are VPN servers which are, by the term themselves, are usually not called an access concentrator, but what they do is pretty much the same. And of course, in the ISP world, PPP Yui server, so-called broadband remote access concentrators, or BRAS, and that's the two that we really want to focus on during my examples. Before we do so, I want to explain that there are multiple scenarios where you will have many access concentrators in a row. They're all taking different, or they all have different usage, and they will all be necessary for your service to run. So operation of all access concentrators is relevant for your service. This is an example that you will, for example, find in a network of Deutsche Telekom when they have resellers on their DSL access nodes. Those resellers, or the traffic of those resellers, has to be forwarded to their own layer 2 network, and they will split the username and forward the traffic based on the username. So that's what's happening here, and you have 3 access concentrators to do so. You have an LAC, a layer 2 access concentrator. It aggregates the PPP Yui sessions of one access node and forwards them through a layer 2 tunnel to an LNS. And the LNS will be the next concentrator you have, aggregating all the layer 2 sessions. And finally, after the LNS, you have the BRAS or PPP Yui server taking care of all of the PPP Yui sessions. So all 3 concentrators have to operate or have to run for your service to be on. So that leads to a couple of considerations. An access concentrator will service a lot of users. Its failure is critical, it's service affecting. Quite often it's a single point or central single point of failure. And on the hardware side, access concentrators might demand a lot of system resources. Like, for example, PPP Yui servers are quite commonly the bottleneck in an ISP network, as they have a high throughput, a high number of packets, and the CPU usage might be the bottleneck for an VPN access concentrator if it's not using hardware encryption, for example. So taking these considerations into account, on one hand, we saw it's a critical single point of failure, so we want to have redundancy for this node. It demands a lot of system resources, so it would be quite well to have load balancing so we can scale our network. So the best approach definitely will be to have a combination of load balancing and failover, since this will account all the considerations we took. I want to show 2 different industries now. The first 2 examples will be for enterprise customers running VPN, and the second 2 examples will be from the ISP world for a simple and a complex ISP setup using PPP Yui. A typical enterprise setup might look like that. You have your remote clients at the right hand connecting through the internet to your local VPN server, which is quite commonly placed in the DM set of your network. We will simplify this a little bit to make the examples more easy to understand. So we are running the VPN server directly on our broadband gateway. So this guy here is a broadband gateway with integrated VPN server. On this setup, you can clearly identify 2 single points of failures. It's the router himself and it's the broadband line. So these 2 elements should be covered by a failover concept. During the next examples, I will assume that we took all the advanced configuration that is necessary for a gateway. We don't want to run through all of that. We just assume it has been done. So we have a PPP Yui client running. We did not for PPP Yui. We have our VPN server up and running, like SSTP or whatever flavor you prefer. And on the local area network, we have a DHCP server running in DNS. So we don't want to talk about these services anymore unless there are special considerations necessary during our setup. So the first setup we want to look to is hardware redundancy. Here's the setup we want to discuss. We have two broadband routers with integrated VPN servers, and we want to have them running in a failover concept. So there are a couple of tasks we have to complete. We have to switch between the PPP Yui clients. So in this setup, we're just connecting both routers to one modem. So we have to switch between the PPP Yui clients. We have to select the proper default gateway for the local area network. We have to take into account that we are running two DHCP servers. We have to take care for the public dynamic IP address for the VPN server. And we will consider a special case where not a complete router is failing, but just a LAN cable is being unplugged or a port is failing, since this is a special case during the failover setup. For the default gateway, our LAN devices will typically not support any dynamic routing protocol, so we can't use OSPF or something like that to distribute the gateway's address. So that means the default gateway IP cannot be changed, and both gateways will have to share the same IP address. And this is typically not a pretty good idea in the same network. But there's a special protocol called VRRP, the Virtual Router Redundancy Protocol, which will exactly help you with this situation. It will offer you the possibility to share an IP address between two interfaces or even more interfaces on different routers, and only one of these interfaces will be in master mode, having the IP address being active. Here's just a short diagram on how VRRP works. These are the broadband gateways, and the Ethernet 3 interfaces are pointing towards your local area network. On top of these physical interfaces, you will run virtual interfaces, the VRRP interfaces. And regarding the IP addressing, you will need dedicated different IPs on the two Ether3 ports. So these IPs are from the same IP segment, but it's different IP addresses, in our case 1060.0.1 and 1060.0.2. Both come with a /24 net mask. On the VRRP interface now, you're using the same address for both interfaces, but there you will configure them to have a /32 net mask. So the blue IP addresses will always be active, while the orange one will only be active on one of the routers. So that way VRRP will control which router has the default gateway's IP address, and the local traffic can be sent to that IP address. VRRP will take care of which router will process the traffic. We will see how to set it up in a second. On the outer side, we have a similar problem. There are two routers connected to one modem, and just one of them should have a PPP Yui session running, as your ISP will usually not support more than one session for the same customer. So you have to take care for that too. Actually, we can use, or let's say misuse VRRP for this task too. I'd call it to misuse it, because usually you will not need IP addresses on your WAN interfaces pointing towards your PPP Yui or towards your DSLAM or your modem, as you will receive the address by PPP Yui. For VRRP to run, you will have to set up these addresses, the physical ones and the virtual ones. Before you did that, the interfaces will not be operating. So you will set up this these addresses, and then set the PPP Yui clients on top of the VRRP interfaces. That way, both routers will try to connect, so you will see LCP packets in your log files, But only the router whose VRRP interface is active will really send these packets out of the interface. So the other one will just try it on PPP Yui level, but no interface is leaving towards the modem. So this is the configuration you take here. The Ether1 interfaces pointing towards your modem, and on top of them, the VRRP interfaces. I'm not really sure, I hope you can read the screenshots, it's not very big here, but this is the complete VRRP overview we have for that configuration. And the first line you see the master router, on the second line you see the backup router, and on figure 1 you can see the two VRRP interfaces, one running with Ether1 as a parent and the other one running with Ether3. And on figure 2 you can see for that router that the VRRP interfaces are available, so they can be used. This is the IP which is swapped between the routers. While in the backup router, you can see these interfaces are in backup mode. They come with a B here in the front, and the IP addresses are marked red, so they are not available on that router. We don't have an IP conflict on our network. You can also see that the PPP Yui client is only running on router 1, while it's inactive on router 2. As I said, it tries to send out packets, but the VRRP interface will simply not forward them out of the physical interface. And here's the VRRP configuration, so what we have to do to set it up. In this example, it's for the local interface. There are just a few things you have to do. You have to set up an interface, and physical interface the VRRP is using as a parent. And you will have to set up a VRID, which is a common ID for all interfaces belonging to the same VRRP cluster. In our example, it's only two routers, 2 internal interfaces, but it could well be 3 or 4 or 5 of them. So we have 2 VRIDs, one for the outer interfaces and one for the inner interfaces. Then there are 2 configuration options, priority and preemption, that control which interface will be in master mode and which one will be in backup mode. Typically the router having the higher priority, or the interface having the higher priority, should go to master state. But then again there is preemption mode, and preemption mode will control if a router, if it has higher priority but is in backup mode, for example it was booted later than the other one, if it will force itself to go to master mode, or if it will be happy to run in backup mode, although it has highest priority. This is important for one of the examples with asymmetric traffic flow that we see on one of the next slides. But luckily, that's all you have to do to set up VRRP, so it's rather simple. And once you understand how it works, you will find a lot of use cases for it. So that's what happens if router 1 is up. Router 2 will not have any VRRP instance in master mode, and we will see the traffic flowing from the internet through PPP Yui to router 1 and to our local area network. If that router is power cycled or has a power outage, for example, so the complete router fails, both VRRP instances will flip over to the router 2 with the lower priorities, so everything will still be working smoothly without any additional action to take. But there's one special case that you will always have to take care of when you're using VRRP on more than one interface, like we do here in these examples, and that's an asymmetric situation of VRRP. It happens, for example, if you're plugging a cable. So let's assume this cable here is plugged, or a port is broken on a switch, for example. That means the router is still up, but just the connectivity to the next hop is lost. In that case, we will see the first router be master on the outer side, lose connection here, so the second router will be master on the inner side. And what happens is that inbound traffic will enter the network through router 1, but will not have any way to go to the local area network. And outbound traffic will go through router 2 and will not find a PPP Yui connection to be terminated to the internet. So although there is connection possible, our traffic will not flow. And in all of the VRRP setups, not only in that one where you have this situation with a potential asymmetric flow, you will one possible solution is to use a cross-connect between these two routers. That's what we see here on the right-hand side. We use an additional cable to connect these routers directly, or a switch with a VLAN, for example. So now we have the physical possibility for traffic to flow. But to have it do so, you will have to take care for the routing, because so far we don't have routing between router number 1 and number 2. So you will add some additional routes for the local network and for the default gateway, of course. And these routes shall only be active if VRRP is not working. You will take a higher distance for these routes, so they will only come into place if the main routes are not there. That's what we actually here see here. It's easier to see than to explain. In the first red box, we have the two default routes. One coming from the PPP Yui out 1 interface. It's reachable, so that route has a distance of 1 and it will be active. Then we did set up a second default route pointing to Ether 4, so to the Crossconnect. So if that route is not active, we will take that one. That's what's happening on router 2 right now. It will point to the other one. And in the second red box, you will see the routes for the local network. And here you can see in the second line, the route through Ether 3, that would be the preferred route through VRRP. It's not available as Ether 3 is unreachable, so the route is not active, and it dynamically will get a distance of 255. So it's moving from distance 1 to 255, and by doing so, our route with distance 2 will get active, and traffic can flow from the internet to the local area network. Of course, that's something that you have to do on both routers. There's another case connected to preemption mode that I tried to explain before. In our setup here, if preemption mode is not active on router 1 and you're replugging the cable, what's going to happen? Of course, it has highest priority, but it's not going to take or not going to use its priority to force itself back into master mode. So we still have asymmetric connection, master to the outer side on router 1 and master to the inner side on router 2. But as you replug the cable, the physical connection is back, and the connected route associated to this interface is back in the routing table. So it's not a 255 distance anymore. It went back to 0. So right now you will really have a totally asymmetric packet flow. And on one hand, it's important to understand when you look at your interface counters what's happening. And it's especially important to understand if you're having sophisticated firewall rules, as you really have to understand why and where packets in what state are coming from. And what's happening here is traffic is entering through the PPP Yui connection on top of the VRRP, on top of the Ethernet interface. That's what you see in figure 1. And it's not using the cross-connect, but it's leaving through the connected route on Ethernet 3 to the local network, and then it will flow to the other router according to the default gateway, and along figure 3, and then along the cross-connect and out to number 5. So you will see packets flow asymmetrically, and you have to take that into account. If you don't want to have that, enable preemption mode, and it's not going to happen. So now we took care of the VRRP connections, inner and outer side. I explained the problems or the potential problems with VRRP. Let's have a short look at the DHCP servers. We have 2 routers, and both of them are offering DHCP, which is not a problem in general, but you have to take care that you're not handing out the same IP address twice. For example, router 1 might hand it out, then VRRP flips over and router 2 doesn't know about that lease and it might hand it out again. The DHCP server can also be run on VRRP, so it's not operating anymore if you're not running or if the interface is not running. And the trick here is pretty simple. You just go there and split your pool that you use. If you need 50 IP addresses, dynamic ones, for example, use 50, like in this example, 50 to 100 in the pool of the first DHCP server, and another 50 in the pool of the second DHCP server, so they can flip forth and back, and DHCP will always working. To have your VPN operating with dynamic addresses, you have to take care of the dynamic IP address, and your VPN clients have to know it. So the idea here usually is to use an FQDN, so you set up a domain name, a fully qualified domain name, and not an IP address for your clients. And you update DNS once the IP address changes. RouterOS has an integrated DNS facility called IP Cloud, but it's not going to do the job in this case, as IP Cloud will set up the DNS name automatically based on the serial number. And if we as we have two different routers with two different serial numbers, this will result in two different domain names, so we do not have this common FQDN to set within our VPN clients. There's a whole bunch of alternative DNS services available. I'm choosing Change IP here in my examples, but you can choose any that you like. Change IP is using the integrated tools DNS update facility. Other approaches will use tools fetch. You can see the wiki for a whole bunch of potential scripts. Be aware that there are always different versions for NAT and not NAT situations, and the NAT aware scripts will write on your disk. So if you don't need the NAT version, go ahead with the standard version. And whatever you do, take care that you encrypt your DNS updates, as you will have to send username and password of your service. And if someone gets hold of that, he can disable your complete VPN by setting a wrong IP address on it. You can see the script in the wiki or later in the presentation. It's just here for reference. So we're done with this first example now. What we did is we switched between two PPP Yui clients by using VRRP. We selected the default gateway for the local area network by using VRRP. We saw how to take caution for two DHCP servers. We have a solution for dynamic public IP addresses on the VPN server, and we had a look at the special case of not a router failing, but just a cable being unplugged. So by now you have hardware redundancy in place. There are a few optional steps you might want to take. For example, we didn't talk about the VPN accounts that should be transferred from one server to the other. There might be static DHCP leases that should be transferred between the servers, and maybe even static DNS entries. It's not part of the presentation, but you can use import and export scripting, for example, to transfer these information between the routers. The second example, still concerning VPN, but this time we will take a look at redundant access lines. A broadband connection is, well, not failing regularly, or well, probably depending on the country and the carrier, but usually they're quite stable. But still, the broadband connection is a single point of failure. And now we have a look at an example using one router with two broadband connections. We still use PPP Yui on DSL and dynamic public IP addresses. What we want to approach, and this is a quite common thing customers want to have, we want to use both of the DSL lines, and we don't want to simply load balance, but we want to do, let's call it an application-based load balancing. We want to use ISP1 purely for VPN traffic and ISP2 for the standard local area network traffic. That's what you see here, VPNs through ISP1 and the other traffic through ISP2. So that's the goal of the upcoming configuration. Redundant internet access. We want to implement real advanced line checks, which is not that simple to do. We want to have inbound VPN with dynamic IP addresses, and we want to balance our two lines based on the application. VPNs on ISP1 and local traffic or non-VPN traffic on ISP2. First thing to do is to take care that ISP2 is our default outgoing internet service provider. So we use the default route distance configuration option in the PPP Yui client. If you set the default route distance to 2 for ISP1, ISP2 will always be preferred. So that's more or less a gift. There's nothing else to do to send traffic out ISP2. And if the ISP2 PPP Yui connection fails, we get fallback to the other line automatically, because if the connection fails, the interface will not be available. Its route will vanish, and that way we will automatically take the default route with the higher distance. That's what you can see here, just one default route left. The problem though is that the ISP might not necessarily fail with the PPP Yui connection, but for example there might be a routing problem within the ISP's network. So that means your PPP Yui connection is running, it's up and fine, and you can even use check gateway or whatever to check its gateway. But if you have a problem within the ISP's network, you will not find out. You will simply route your traffic to that ISP, but it's not going anywhere. So what you really want to do is you want to have a real line check, really check if that ISP is available, and the solution for that is called NetWatch. It's a very simple facility. It's more or less pinging a given IP address and offers you up-down scripts to run if NetWatch is successful or not. But with 2 lines, it's not that easy to implement. You have to take quite a few steps to make it work properly, and that's what we want to do now. We will implement NetWatch and force the check to use a dedicated line and really test for the real availability of these 2 internet service providers. In our example, we will use Google DNS 8888 for ISP1 and 8844 for ISP number 2. And we could force the traffic to go through a given internet service provider by simply using a static route like that. But that's not really nice, because if that ISP fails, for example ISP1, 8888 will be rendered unusable for the complete network. And maybe you have a client computer in your network using this DNS server, and by that line failing, the DNS service will not be available anymore. So it's a pretty bad idea to simply use static routing. And the best approach here is to use the Mangle facility. It's part of the firewalling facility in IP firewalling, and to use extra routing tables. We can set up Mangle rules, as you see here in the screenshot, in the output chain to the destination 888, and we can limit that rule on ICMP packages. That way we have 2 advantages. It's not accounted for packets coming from our local network because we're in the output chain. And it will only be used on ICMP packages, so the internal network and even DNS service for the local routers are not affected. After mangling these packets, we will force them to use a different routing table. So we add 2 routing tables, I'll show you in a second. We do the same thing for 8844, and here are the 2 routing tables that we're using and that we want to have the Mangle facility point to. The upper one for ISP number 1 is having an alternative default route. So packets to ICMP packets from the local router to 8888 will be mangled, will be using this default route, and will be sent out to ISP1 if the PPP Yui interface is active. If it's not, this default route is going to vanish, and the routing decision will automatically fall back to the default route from the main routing table, and that's actually not what you want. That's exactly what we don't want to happen. So please add this black hole route with a higher distance here. Black hole routing is routing without a gateway interface, and that means this black hole route is always active. So if the default route in this special routing table vanishes due to the interface is not there, the black hole will still be there and make sure your packet is not going to the main routing table, so it's not being forwarded. So now we can test our pings to the 2 different locations, and we will see we are using the correct ISP. But if you're switching forth and back, you will see there is kind of a tricky problem. And honestly, I can't explain you why it's there. I'm not really sure if it's even a bug in the kind of complex routing decision. The problem is that we are sending packets to two different lines. The source address will always be the IP address from the default route in our main routing table. As we are using different routing tables, we'll be using different output interfaces. So for one of these both connections, the router has to do network address translation in order to rewrite the source address. And it does so perfectly fine in the first place. But now when you start to swap lines, it's not always taking track that it has to swap what connection has to be source nutted. And that's what you see here. Here are our two connections. And you see which is correct. They are both shown with the same source address because that's before NUT takes place. But none of these connections is source nutted. If it was source nutted, it should read SCS with a small s for source nut. So at least one of them should be source nutted, but as you can see, the router didn't track the swapping of the lines. So what happens is it's still using the correct output interface, but on one of the interfaces, it's using the wrong source IP address, so the packet will come back on the other interface. So now suddenly your check needs both ISPs to be operating, and it's not giving you the result you wanted to have. You can clearly see that here with a torch on the PPP Yui interface. We see packets to both targets being answered to the same source address. So the problem is absolutely obvious. There's an easy solution for that. As I said, it shouldn't be necessary from my point of view, but it's still working. You just add two additional source NUT rules, and you will add these rules in the source NUT chains as you're used to, but you will set them only for the routing mark ISP1 or ISP2. So use the routing mark you set before to force the router to reconsider his wrong NUT decision and finally masquerade the packet. So these two helper rules will make our NetWatch work perfectly and keep track of any line change that we have. So finally, we create the NetWatch scripts or the NetWatch tests, integrate up and down scripts, because in the first place we wanted to use NetWatch to swap the distance of the default route, and that's what we do here. But we'll run into another problem, and it's again a connection tracking issue. That time everything works as it should, but you have to take care of a special situation, especially if you're running NetWatch. So imagine you're running a ping with a standard delay or a standard timeout of 1000 milliseconds. So you fire up a ping every second, and the default ICMP timeout in connection tracking is set to 10 seconds. So this connection in the connection tracking list will never vanish. It will always be there as you trigger it all the time. So now when you swap ISPs, connection tracking will be lost. It still has the old connection tracked for the old ISP, but you're swapping default routes and the connection tracking is not showing the correct entry anymore. The solution to this is rather simple. As we're swapping default gateways based on the NetWatch script, we can simply add 2 more rows to the NetWatch, a short delay to be sure things are working out, and then finally reset the connection tracking with this command line here. So if you add that to your script will trigger a NetWatch target not to be reachable anymore. It will change the default route distance, have a short delay, reset the connection tracking list. So the connection tracking will see the new connection going out of the new interface and everything's fine. But we are still not there. So now we need change IP again to set up the IP address, as we want to have SSTP inbound on interface 1. And this time we will have to modify the script a little bit. The standard script will use the interface whose IP address shall be set as a preset in the script. And we will modify the script a little bit. You will see the complete one in the presentation. And we will use the interface being set from a global variable. If it's not set, we will use a preset of PPP Yui out1. Here's the complete script. You can have a look at it in the presentation later on. And now we set up a second NetWatch instance for ISP1. And that one is only meant to change the global variable for the change IP script to point to the right interface. If ISP1 is up, we want to use ISP1's public IP address. If it's not up, you want to use ISP2's public IP address. So we set the global DDNS interface and finally run the change IP script. Now inbound SSTP will be on ISP1 if both ISPs are up. Please remember also to set a scheduler for the change IP script, as there might be regular changes caused by your internet service provider. But we will again end up with an asymmetric packet flow. SSTP is using ISP1's public IP address entering our router, and packets out of the networks are sent along the default gateway pointing to ISP2. So that's still not what we want, as the load sharing of our two lines is far from perfect. Let's again use Mangle, as it's, well, it helps us in this setup a lot, and Mangle is also the solution to force new connections coming in ISP1 also to leave through ISP1. We will first set a connection mark for new connections, and then we use that mark to set a routing mark. Here's the connection mark at first. In the first red box, you see we're in the pre-routing chain and use the PPP Yui interface and only new connections, that is, connections established from the outside to our routers, like the VPN connection. And these connections shall be marked with our connection mark SSTP. In a second Mangle rule, this time for the output chain, we will only look at these connections we just marked, and we force them to the alternative routing table that we have used before, the ISP1 only. So that way you make sure if ISP1 is up, if its IP address is being used for the FQDN and SSTP is going in that interface, it will also leave through that interface. If we are on ISP2, we have the different FQDN. These Mangle rules are not in place, and SSTP will use ISP2 along with the rest of our traffic. So we're actually done with the setup of redundant lines. We selected the preferred line for non-ISP traffic. We implemented real working advanced line checks for the two ISPs. We sorted out all NAT and connection tracking issues that we had. We worked with dynamic IP addresses for the FQDN, for VPN. We made SSTP stick to its interface and finally implemented redundancy for both lines, so both applications, local traffic and VPN traffic, will always be working. Of course, you can combine what we've seen in these two examples so that you will have redundant hardware and redundant lines. In reality, there are always a lot of circumstances that you have to consider, and I try to show you some of them. Maybe you want to add an LTE connection, for example, to have media redundancy too. So you're free to change that to your needs. So now actually I have 5 minutes left to show you two more examples. So I'll run through one of them. So we have a couple of minutes for the last one of them, and that's ISP networks and PPP Yui access concentrators. We make this very fast. I guess most of you know what PPP Yui is, and there's one important thing we will need in layer 2 connection to connect our client to the PPP Yui server. So usually you will have, no, it's not on that slide. Usually you will have a virtual layer 2 network between client and server. Typically you will have many users. You have a high system load on a PPP Yui server, and due to the fact of the layer 2 network, you will also have to take care of Now I'm getting too fast, I'm 2 slides ahead. Oh, sorry. You will have a large and frequently changed user database. When running redundant PPP Yui, the user database is definitely a topic to look into. It's a critical single point of failure and it needs lots of system performance. So this time we should not only implement failover, but load balancing would be really good to have. And as I said, we need a layer 2 network. We will typically not have a huge layer 2 network in our ISP, but we'll use something like EUIP or VPLS to have a virtual layer 2 network. And that will mean we might have another concentrator to concentrate layer 2 traffic, and that should be redundant too. I will actually just very short show you the simplest setup for an ISP that will give redundancy on the PPP Yui. It's actually still running for quite a few customers we have, so it's simple, but it's still real. You can use Ethernet over IP to have a virtual layer 2 network between aggregation routers and PPP Yui servers, and the PPP Yui session will run through Ethernet over IP. And again, you can use VRRP on the inner side. So the VRRP IP address is the endpoint of your Ethernet over IP tunnels. That's basically the main concept of this simple approach. So multiple PPP Yui connections will go through each of the EUIP tunnels, and if one of the PPP Yui servers fail, VRRP will flip over. It will take all the Ethernet over IP tunnels with it, so we have redundancy for the BRAS. On the upstream side, we will assume for this simple ISP that our upstream ISP will route our complete IP network to our PPP Yui server, and we can use VRRP again to offer a gateway address for our ISP. So the routing of address space will also flip with the VRRP interface. And again, we have that example of asymmetric traffic flow in the situation that VRRP is asymmetric internally and outernally. And we've already learned that we can simply use additional static routes and a cross-connect here at number 1 to fix that. In such a simple setup, you might want to use User Manager, for example, as a very easy to set up AAA solution to authenticate your users. And you could consider scripting to copy the User Manager database between your routers, so you really have the full failover. So now let's take the last couple of minutes to look to a more sophisticated internet service provider setup offering load balancing and failover at the same time. This is a bit more complex, so I want to introduce the network first from right to left. We have the 2 internet service providers, 2 upstream providers, and we use BGP in this case with 2 BGP routers, 2 upstream switches, 2 PPP Yui servers, 2 backbone switches. Then we will have 2 radio servers for our network, and finally 2 VPLS endpoints to terminate the layer 2 sessions. And afterwards, on the left-hand side, we run into our own backbone towards our customers. Connectivity will look like that. Actually, of course, we could use stackable switches, but we want to do this example with MikroTik, so we use 2 switches, and the different colors indicate that we are not in one layer 2 network, so we have 2 interfaces on the BGP routers. There will no loop prevention be necessary here, as it's 2 layer 3 networks. A short look at the 4 segments from right to left. At first, 2 internet service providers connected to each of our BGP routers. Usually you will prefer one of your ISPs by prepending the other one. And by connecting both of them to both routers, you can be sure that your preferred ISP will still be available if one of the BGP routers is failing. If you have a preferred router, hardware-wise, depending on your BGP partner, you can use communities to make them prefer inbound traffic to one of your routers. So more interesting is the area between the BGP routers and the BRAS or the PPP Yui servers, as you will have routing issues here to solve. On one hand, you have to propagate your default routes from the two BGP servers, and you can simply use OSPF to do so and propagate default routes all the way to the PPP Yui servers. It will end up in an equal coast multipath routing, so both BGP servers are used for outbound traffic. And as we said, we want to implement load balancing. We cannot say in before which IP address of which client is going to pop up on which of the PPP Yui servers. So we have to have a mechanism to take care for the route for the PPP Yui client. And we are also going to use OSPF here. If a client is connected to a PPP Yui server, you will have a /32 IP address pop up there, and OSPF can propagate this information to the BGP servers, so the routers, so the BGP routers know to which BRAS they have to route the packet for that PPP Yui connection. Finally, we have our PPP Yui servers using two radius servers. Typically, you will use MySQL replication or any database replication to replicate the user database, and you will simply configure two radius IPs on your MikroTik PPP Yui server. If free radius with replication is too complicated to set up for you, if you don't want to waste your time for that, there's a ready-to-run alternative called HSNM. It's a ready-to-run appliance, and the vendor is here in the exhibition area, so you can chat with them or with us if you're interested in it. Here's a short view of the user interface, but as time is short, we don't want to spend too much time to it. So any form of replication will be necessary to use two radio servers and be redundant here too. So the main concept of load balancing is actually working out of the box, as you can simply put multiple PPP Yui servers in a layer 2 network, and when the clients send their PPP Yui discovery, broadcast their PPP Yui discovery, whatever server is first answering this discovery packet will take the connection. Typically, if a server is having higher load, more packets for example, it will be slower, so we have a natural distribution of client connections through two or even more PPP Yui servers. So that's how we achieve the complete load balancing and failover on PPP Yui. And the end of the network is the VPLS access concentrator. As we said, we need layer 2 connections to the PPP Yui server. We will use VPLS access concentrators, again with a VRRP interface as an endpoint for the VPLS termination, as that concentrator needs to support failover too. And my colleague Sebastian is going to show that example in his presentation later today, so I will not discuss about that in details. And we will end up with a perfectly purely MikroTik core of our ISP, and you can have lots of components fail and still have load balancing and failover of the BRAS working. And VPLS point, one of the radios, an upstream switch, a BGP router, and one of the ISPs can fail at the same time, and your network is still working, and still both of the PPP Yui servers can handle your traffic. As I said before, the very end, the backbone of this network is going to be part of Sebastian's presentation at 2:15. And I see Normus is getting nervous for me shooting over time, so I'll end up my presentation here. I hope you picked up a few ideas for yourself, and I hope you will enjoy the rest of this great user meeting. Thank you.